Hello. Today we're going to think about how big is the universe, and we can answer that question straight away by saying we don't know, and we can't know. Before we explore further, we have to think about how we are going to model the universe. One way of doing it might be simply to consider the universe as a large sphere. But actually that's not a good way of thinking about the universe, because it implies that if you are at the edge of the universe, you look out on nothing, whereas all the stars and the galaxies are here. But that is not a proper model of the universe. The universe is regarded as what is called homogeneous and isotropic. Everywhere looks the same. And that means that there is no edge to the universe. You might wonder how you can have no edge. And it's quite difficult to explain that in a three-dimensional world. But think for a moment in two dimensions and think of the surface of a sphere, or if you like, the surface of a balloon. Where is the edge of the surface of that balloon? The answer is it doesn't have one. If there is an ant on that balloon and he wanders about, he will never ever come to an edge. He can keep walking forever around the balloon. There's no edge. And in two dimensions, the surface of a sphere or the surface of a balloon serves as a very good analogy to the space in three dimensions, which has no edge. What we can consider is the observable universe. That is the universe that we can see. Now this truly is a sphere with us at the centre. It doesn't mean that there's nothing beyond that sphere. There is. It's just that we can't see it, because a point at the end of the sphere is the furthest point that we can actually see. The reason it is a sphere is that because the universe is homogeneous and isotropic, it means that all directions will appear to be the same, and that means that the maximum distance that we can see will always be the same in all directions. Now you might consider that the radius of the observable universe is 13.7 billion light years, on the basis that light has only had 13.7 billion years to travel from here to here, and travelling at the speed of light, that means it would cover a distance of 13.7 billion light years. But once again, you would be wrong, and let me explain why. Once again, I want to consider a balloon and an ant walking on the surface of the balloon. Let us suppose that there are 2 points on the balloon, A and B, and that they are 10 centimetres apart. And we say to the ant, we want you to walk from A to B, and the ant travels at 1 centimetre per second. Now the ant will say, that's fine, I can travel from A to B, and at 1 centimetre per second, that will take me 10 seconds. But rather cruelly, as he begins to walk along that line, we start to blow up the balloon. And we blow up the balloon such that it doubles in size every 7 seconds. What will happen? Well, let's think about what happens 7 seconds later. A to B will have been stretched because we've blown up the balloon, and it's doubled in size. So now this distance is 20 centimetres. How far will our ant have got? Well, you might think that he will have got, in 7 seconds, 7 centimetres. But actually, of course, this space, in fact, has been expanding as well whilst he's been walking. So he has been, in a sense, carried along by the expansion of the balloon as well as his own walking speed. So he probably have got to a point 10.5 centimetres along. And now he's got 9.5 centimetres to go. But of course the balloon is still expanding, so 7 seconds later, A and B are now 40 centimetres apart. Where has the ant got to? Well, let's just think for a moment. Suppose he had stood still at this point. Then he would be at 21 centimetres along the line, simply by virtue of the expansion of the balloon. But in those 7 seconds, since he's walking at 1 centimetre per second, he will get to the point 28 centimetres along the line, and of course that will have stretched as well, so he'll probably get to a point 31.5 centimetres along the line, with 8.5 centimetres still to go. Another 7 seconds later, and the balloon has stretched again. Now A to B is 80 centimetres. And where will the ant be? Well, if he stood still at 31.5, then he'll automatically find himself at a position 63 centimetres along the line, because just by standing still the balloon stretches and doubles in size, and he will be at the same proportionate point as he was here. But he is, after all, moving at 1 centimetre per second for 7 seconds, so that'll get him to the point 70, plus the stretchy bit here gets him to 73.5. And now he only has 6.5 centimetres to go. And now, 7 seconds later, the balloon doubles again. And now it's 160 centimetres long. And the same principle applies. If he stays where he is, he'll just be at 147. But he adds another 7, that makes 154. Plus the stretchiness, he's now at 157.5. He's only 2.5 centimetres away. 7 seconds later, it doubles again. Now it's 320 between A and B. Once again, if he stood entirely where he was, he would end up at 315, because the balloon would stretch and double its size. He's only 5 centimetres away, so in the next 7 seconds, he will reach point B. But look, it's taken him 1, 2, 3, 4, 5 lots of 7 seconds. It's taken him 35 seconds to travel what he thought would only take him 10 seconds to travel. And when he finishes, the point A from which he started and the point B at which he ends is 320 centimetres apart. If he had taken a photograph at A and brought it with him all the way to B, then the people at B would see what A was like 35 seconds previously. Now hold that thought, because it's very important for what we shall see about the observable universe. By contrast, however, let's just imagine that self-same ant with a line on the balloon that's 10 centimetres apart between A and B, but this time the universe doubles every 2 seconds. Well, 2 seconds later, the universe will be 20 centimetres, or his line will be 20 centimetres across. He will only have covered 2 centimetres, plus a little bit of stretchiness, let's call it 3. He's still got 17 to go. 2 seconds later, the universe has doubled again. It's now 40 centimetres long. If he'd stood still, he'd be 6 along, plus another 2, because he's walking at 1 centimetre per second for 2 seconds, plus let's say another 1 to account for the stretchiness here.